This is video 2 for the Gravity, Force, and Space Unit. So in the last one, we left off saying that the reason why astronauts are weightless is because there's no normal force acting on them. So the way we feel our weight is by having something push back up against us, pushing up on us. And we call that something normal force. So suppose you're in an elevator and the cable breaks. The elevator and you begin to fall. The normal force that was once acting on you goes away because, the thing pushing up against you is no longer pushing up against you. This causes you to feel weightless. So even though the Earth is still pulling on you with the same force that it always does, because there's nothing beneath your feet pushing up against you, you suddenly feel weightless. Now, imagine that elevator never hits the ground. You would have the sensation of weightlessness indefinitely. That is how astronauts achieve weightlessness. So, we just have to figure out how they fall without ever hitting the ground. Imagine that on the Earth we have a very, very tall tower. And on top of this tower we have a cannon, and we launch a cannonball. This cannonball initially follows this kind of path, kind of a parabola. Okay, now imagine we give it an even greater velocity, so we pack more gunpowder into it. Then we fire the cannonball. It's going to go a little further and eventually hit the ground. Okay, we're going to put even more gunpowder in it. And go even further. Now imagine if we were to put enough gunpowder in it that when we fire this cannon, as this projectile falls, it completely misses the Earth. It just continues to fall around it. That is how astronauts stay weightless. They don't fall to the Earth. They fall around the Earth. So, at the altitude of the International Space Station, you would probably feel about the same. If we built a tower that, if the top of the tower was at the International Space Station, if you were to stand on there, you probably wouldn't notice any difference in your weight at all, because it's only a 5% difference. However, because the astronauts are constantly moving around the planet, they're constantly falling to the Earth, but instead of falling and crashing, they're falling around the Earth. They do not have that normal force pushing back up on them, and it causes them to feel weightless. So, the International Space Station is in what we call low Earth orbit, or LEO for short. It's a circular orbit, a few hundred miles above the surface, and in order to do this, to fall around the Earth, it has to move at a speed of 8 kilometers per second, which is 8,000 meters per second, which is roughly 18,000 miles per hour. They are moving fast. At this velocity, the satellite orbits the Earth in 1.5 hours. And the Earth has a circumference of 24,000 miles. So this thing is going 24,000 miles in 1.5 hours. That is fast. So let's say we have a space shuttle, and the astronauts inside the space shuttle or satellite, they want to land. They do not fire the rockets in a direction away from the Earth. What they do is they fire the rockets in the direction they're going, because right now they're moving incredibly fast. So what they do is they have like these retrograde rockets, and they fire them this way to slow the spacecraft down, and that causes them to lose orbit. Generally speaking, there's these specific speeds for these specific orbits. So to be in low Earth orbit, you must travel at 18,000 miles per hour. Any faster, and you'll go to a higher orbit. Any slower, and you'll begin to fall back to Earth. So, now, as you might imagine, we don't want to stop the satellite completely, because if you stop completely, then you're just going to fall straight down. So if the satellite moves faster than 5 miles per second, it's going to leave its circular orbit and head out to space. And then at 7 miles per second, it's going to have a sufficient velocity to reach the moon. And that's what we call escape velocity. And that's actually something I believe I derived for you in class. All right, so that was low Earth orbit. The next type is geosynchronous. So these ones are where we place our weather satellites and TV satellites. They have a very special orbit. We call it geostationary. So that means that they stay above the same location of the Earth at all times. So you may be wondering, well, how can this be, since a satellite must orbit the Earth to avoid crashing back down? So you have to remember that gravity follows the inverse square law. It becomes weaker the further away you get from a planet. So a geostationary orbit is at a distance of 22,000 miles, and because gravity is weaker there, the satellite does not need to travel as fast. So for this one, it takes one of these satellites 24 hours to orbit the Earth. Yeah, this is something we're going to discuss in class a little bit more. But, it takes 24 hours. So if it takes 24 hours to orbit the Earth, if you think about it, that means that it's going to stay at the same location above the Earth. And again, we'll talk about some uses for this in class. Spy satellites. These ones are fun. A spy satellite is something that carries a telescope to look down on the surface of the Earth. Yeah, see what's going on. Now, an ideal spy satellite would stay above the same location at all times. So you would think the ideal spy satellite would be a geostationary orbit. However, to do that, again, it would have to be 22,000 miles away. And at that distance, even our best telescopes cannot resolve anything smaller than 20 feet. So, that means that a spy satellite, you could see a football stadium, but you couldn't tell if a game was being played. Because of that, all spy satellites must be in low Earth orbit. They can't be any further away because they wouldn't be able to resolve the images they're looking at. You wouldn't get any useful data from them. The next type is a GPS satellite. This is in a medium Earth orbit, MEO. So GPS obviously is Global Positioning System. It's what we use to give a precise location on the surface of the Earth. Most of your smartphones will have some sort of GPS receiver built into them. So, a GPS receiver, something that's you have in your pocket, it's going to pick up signals from 24 to 32 different satellites orbiting the Earth. This receiver then determines how far it is from that satellite by measuring how long it takes for a signal to reach it. Then it uses the distance from several satellites to triangulate its position. Now, again, you would think a geostationary would be best, and it probably would be, but long-range satellites like those take too much power to send a signal, especially something small like a smartphone. The low Earth orbits, they travel too fast to send and receive those signals. The low Earth orbit, it only takes a few minutes for it to go past the horizon. That's another challenge for spy satellites. They only got a few minutes to take some pictures, then they're gone. So the GPS will be in medium Earth orbit. They are 12,000 miles away, and it takes them about 12 hours to orbit the Earth. So they can go around the Earth twice in one day. And here's just a simple little graphic. We got several satellites. They're sending and receiving signals from a receiver, and by using time and known distances, it can triangulate. All right. We've done some similar calculations to this in class. Suppose we want to escape the Earth. We want to leave it completely. Just going into orbit isn't enough. You have to get further away. If you want to take a trip to the moon or Mars or some distant star, it's going to take a lot more energy than just going into orbit. So we want to find out how much more. As it turns out, it takes exactly twice as much energy. So remember that the energy we're talking about really is kinetic energy. And kinetic energy is 1/2 mv squared. So if we need twice as much, if we need 2 times the energy, you remember kinetic energy is proportional to v squared. So if I need twice the energy, the velocity would need to be really the square root of 2. And the square root of 2 is equal to 1.414. So what we need to do is we need to travel 1.411 or 1.414 times faster. So orbital velocity is right around 5 miles per second. So I need to take 5 and I need to multiply it by 1.414. So if I travel at 7 miles per second, that will give me enough velocity to escape the planet. And like I said, we did a calculation similar to this using conservation of energy earlier. Now, just like orbital velocity, the escape velocity doesn't depend on the mass, which is nice. So the next thing is, how much energy is there in an object that's moving that fast? Well, kinetic energy is 1/2 mv squared. So let's say we have 1 gram of substance. And we've got to convert that into kilograms. And then 5 miles per second is the same thing as 11,000 meters per second. So when we plug those two numbers into our formula, we find that the kinetic energy is 60,000 joules. And that's about the same thing as 14.5 food calories. So, yeah, we could basically say it's 14 calories per gram. And really, that's only 40% more than the energy in a gram of gasoline. So really, if you think about it, a couple grams of gasoline should be able to put you into orbit. But it doesn't quite work out that way. There's efficiency things, and there's other roadblocks. But it's kind of interesting to think about, how much, just put things in perspective, how much energy we have in things that move, and how much energy we have in like things we already have, like gasoline. All right, that's going to conclude video 2.